Today, we're going to talk about how to create an exponential equation if given 2 points. We're going to talk about exponential and logarithmic graphs and asymptotes. First, let's review what an exponential equation looks like. We can write it as y equals a times b to the x. Y would be money or maybe the current population. A is the start. That's at the beginning when x is 0. That's the y-intercept. B is the common ratio. Common ratio is current divided by previous in an exponential equation. When I look at the y values, the current divided by the previous will create the common ratio. Let's build a table on this exponential equation. Notice if I plug in x is 0, 1.5 to the 0th power is 1 because anything to the 0th power is 1. And 20 times 1 is 20. When I plug in 1, 20 times 1.5 to the first is 20 times 1.5, that's 30. When I plug in 2, it's 20 times 1.5 to the second, which is 20 times 1.5 times 1.5, which is 45. And when I plug in 3, 20 times 1.5 to the third, that is 67.5. The important thing to note is that the common ratio is what you multiply by to get the next value. Notice that when I go from 20 to 30, 30 is 20 times 1.5 once. That's the common ratio, 1.5, right there. 1.5, that's the 1 plus r, where r is the rate or the percent that you're growing at. In this case, it's 1 plus 0.5, 0.5 being 50%. I'm growing by 50% every time. To see how half of 20 is 10, and 10 plus 20 is 30, half of 30 is 15, and 30 plus 15 is 45, and half of 45 is 22.5, and when I add that to 45, I get 67.5. For what we're going to do here in a moment, the thing you need to understand is that each time I move forward 1 in x, I multiply by the common ratio one more time. As I move forward, I keep multiplying by that 1.5 in this case. What I want you to think about is, what if we didn't know the equation, we just had some values, could we figure out that common ratio? To do that, what I need to understand is that in the table, this value here, the second value past the 20, is 20 times that common ratio. I'm going to call it B. The next value is 20 times the common ratio times that common ratio again. And this last value is 20 times the common ratio times the common ratio, and one more time again. This right here gives us an equation that we can solve. That would be 20 b to the third equals 67.5. I could divide both sides by 20, and I get b cubed is 67.5 divided by 20. I want to know what b is, that common ratio. To get rid of a cube, you use a cube root. To get rid of a square, you use a square root. To get rid of a fifth power, use a fifth root. So here we use a cube root of both sides, and then we go and punch that into the calculator, or Desmos. Here we can see in Desmos that the cube root of 67.5 divided by 20 is, in fact, 1.5. In this case, we would know what the equation is because we know the y-intercept is sitting right here. That means we could go y equal 20, which is the y-intercept, times our common ratio, 1.5, to the power of x. X is time again. And I will point out that to get that 1.5, if we had consecutive values in our table, we wouldn't have had to do all this fancy work. And that's because the common ratio is current divided by previous. Notice that 30 divided by 20 If I pick any value, I need to have a previous, so I've got to start at 30. 30 divided by 20 is 1.5. 45 divided by 30 is 1.5. 67.5 divided by 45 is 1.5. If I have consecutive values, I can just divide a current value by a previous value, and I get that common ratio. But if they're not consecutive, then I've got to do what we just did over here. Let's use what we just learned to find an exponential equation that passes through 2 points. Here I've just made up 2 points, and I'm going to find that equation in the form of y equal a times b to the x. First thing I need to do, though, is find that common ratio, that b. I know that this is an x and this is a y, but a good way to think of this that might help you is to think of it like time and population. Time and population, or time and money. At time 8, I have a population of 20. And I know that, think of that table we just built. Every time I move forward one position with x, I multiply y by the common ratio. So I'm starting at 20 here, and I multiply by the common ratio. We call that b by b. So when at time 9, I multiplied it once. At time 10, another time. At time 11, another time. And time 12, and time 13, and time 14. And the result of multiplying by the common ratio all these times is a population of 100. The thing I want you to observe is that all I need to do is to figure out how many times I multiply by the common ratio is just to look at the time. I just take 14 minus 8, and that gives me 6. That's how many steps I take to get from 8 to 14, and how many times I multiply by the common ratio. In other words, my equation is 20 times b to the power of 6 equals 100. Now I can solve for b by dividing both sides by 20. B to the 6 equals 5. That ended up nice, but if it's a fraction, you just plug the fraction into Desmos. To get rid of a sixth power, I use a sixth root, the sixth root of each side, and I'll plug this into Desmos. On your assignment, I have you round to the thousandth. That's the third decimal spot. Notice that past the 7 is a 6. That means it's going to make that 7 and 8. 1.308 is my common ratio. And we're just going to use this, even though it's rounded, it means our equation is not going to be perfect, but it's going to be very close. And I'll be able to tell whether it's correct or not. I'll show you when we get there. Now I know that my equation, the common ratio, the b, is 1.308. And my equation so far is y equal a, that's the y-intercept, times 1.308 to the power of x. All I need to do is find a. Look at this equation. It has an x and a y in it. And notice that I have x's and y's right here. And I know that these points are going to be solutions to this equation. I could use either point. Take your pick. 14100 or 820. I'm going to use 820. Plug it in. Y is 20. I'm trying to find a. 1.308 to the power of x, which is 8. Plug in your x and your y. And then just divide to solve. Divide both sides by 1.308. Don't forget, it's to the 8th power. Both sides. Plug this into Desmos, and you know what a is. A is 2.334 to the 1,000th. We now know our equation is y equals 2.334 times 1.308 to the power of x. How do we check our answer then? How do we know that we're correct? If you go back to our points, if you plug in 8, you should get 20. If you plug in 14, you should get 100. Keep in mind, these values are rounded, so it's not going to be perfect, but it should be close. I plugged those into Desmos to check my answer. I put in x is 8, and I got very, very close to 20. And I plugged in x is 14, and I got very, very close to 100. I know I'm good. There are going to be a few questions on this assignment where you have to plug in values and come up with a couple of points to create a graph. WAMAP makes this fairly easy because you only need to use 2 points. Drag between those 2 points and you got it. I do want to point out that you need to be creative sometimes to make values that work easily in the graph. If you plug in x is 1, x is 2, x is 3, you're going to have horrendous fractions. Remember what a negative power does. When I say 1/2 to the negative first, that negative power flips the fraction. It means reciprocal. That is actually 2 over 1. You can check these in Desmos. You can even make a table using Desmos if you plug in the equation. 1/2 to the negative second would actually be 2 over 1 to the second, which would actually be 4. So when I plug in 1/2 to the negative first, it becomes 2, and then 2 times 3 makes 6. That's why negative 1 is 6. And when I plug in 1/2 to the negative second, it becomes 2 over 1 to the second, which is 4, and 4 times 3 is 12. And all you need are 2 points. And a real easy one to use when you do these graphs is 0. If I plug 0 in, anything to the 0th power will be 1. And for example, here, 3 times 1 will be 3. You only need 2 points to create the graph, though. And here you have an exponential graph, which I attempted to draw freehand. It was fairly close. It is actually decay. That's why it's heading down like that. That's because the common ratio is less than 1. It's 1/2. The last thing I want to talk about is asymptotes. That includes exponential and logarithmic functions. An asymptote is a line that an equation approaches forever. But before we talk about logarithms, we need to remember something about a logarithm and an exponential equation. And that is that they are inverses of each other. Remember how to find the inverse? Let's take a linear example real quick, as in simple example. If I say y equal 3x plus 5, and I plug in some numbers, x and y, when I plug in 0, 3 times 0 plus 5 is 5. When I plug in 1, 3 times 1 plus 5 is 8. Plugging in 2 gives me 11. Plugging in 3 gives me 14. The inverse equation will take this table and flip the output and input values, and the output becomes the input, and the input becomes the output. 5, 0, 8, 1, 11, 2, and 14, 3. Remember that to find the inverse function, what we do is we take and flip the x and y variables. It becomes x equals 3y plus 5, and then we solve for y. Subtract 5 from both sides, x minus 5 equals 3y, and then divide by 3. The inverse equation then is y equals x minus 5 divided by 3. We can check our equation because if I plug in any of these values, the x's, I should get the y's. If I plug in 14, I should get 3. 14 minus 5 is 9. 9 divided by 3 is 3. We're good. I want you to remember that an equation and its inverse are reflections of each other through the line y equal x. Consider the equation y equals 10 to the x. If I want to find the inverse function, what I'm going to do is switch the two variables, x equals 10 to the y, and then I want to remind you how to write a logarithmic expression. This could be written as the log, and the base of the exponential expression is 10. The base of the log would be 10. I know that a log is an exponent, and my exponent is y. So this is the log base 10 of x equals y. Y equals 10 to the x, and y equals the log, and I don't need to put 10 because I know with no base it's automatically base 10. These two are inverses of each other. Now let's take a look at the graphs. Here is the graph of y equals 10 to the x, an exponential graph. And this is the graph of y equal the log base 10 of x. Notice how they're inverses of each other? They are reflections through the line y equal x. And take a look at the asymptotes. For the exponential equation, the asymptote is the x-axis. The equation of the x-axis is y equals 0 because you don't go up or down at all. The asymptote of the log function is x equals 0. It's the y-axis, where x is always 0. Anywhere on the y-axis, x is 0. Notice that I can change the location of the asymptotes just by doing a transformation. If I subtract 2, that'll move the asymptote down 2 to the equation y equal -2, the horizontal line that passes through -2. If I do a horizontal transformation, remember horizontal transformations are the inverse. That's, in this case, moving it 3 to the left. That would be this one, y equals 10 to the power of x plus 3. The asymptotes will change depending on what kind of transformations are performed on the parent function. Here we see the log function and some transformations on the log function. Notice that the y-axis was the original asymptote. That has an equation of x equals 0. What you know is that x will never be 0. That asymptote is what the line approaches forever. And yes, it gets really close to it, but if you zoom in, you'll always see a little space between the line and the asymptote. That's what an asymptote is. It's a line that the graph always approaches. We know that x can't be 0 because it forever approaches 0 but will never actually reach it. That means when I look at this, x plus 3, I know that x plus 3 cannot be 0, and x cannot be -3. That would be this one right here, where the asymptote is actually x equals -3, that vertical line that goes up and down there. And again, it looks like it's on -3, but if I were able to zoom in close enough, I would see that it actually never reaches -3. It just gets closer and closer to it. Notice doing a vertical transformation, moving the graph up and down, that would be this one right here, that's the plus 4, y equal log x plus 4, has no effect at all on the asymptote. If you get stuck on any of these questions, remember to fast forward ahead and look at some of the examples I've done off the assignment. Question 1 off your assignment. You're given a couple of points. You want to find that exponential equation. This is like what I did in the teaching part of the video. You're going to write it in the form of y equal a times b to the x, where y could be population, a is the y-intercept, b the common ratio, and x the time. You could think of it as the population equals the start times the common ratio, that's 1 plus r, to the power of t, where t is time. In an exponential equation, the y is multiplied by the common ratio each time the x-coordinate increases by 1. How many times will 22 be multiplied by the common ratio to become 92? The secret is, think of this as time and population, is to look at the times. From time 12 to time 17, that's 17 minus 12, you multiplied by the common ratio 5 times. Your t is 5. We know that at time 12, we're at 22, and that every time I move one position, I multiply by the common ratio, which I'm going to call B, and from time 12 to time 17, that's the 5. That's our time it takes for 22 to become 92. We're solving this equation. We'll divide both sides by 22 and solve b to the 5th equals 92 over 22. To get rid of the 5th power, we'll take a 5th root, and we'll plug that in Desmos. Round to the 1,000th. B is 1.331 to the 1,000th. Now, we know the equation so far is y equals a times 1.331 to the power of x. All we need to do is go to one of our points and plug in an x and a y. This becomes 22 equals a times 1.331 to the power of 12. And this is time, so we'll divide both sides by 1.331 to the power of 12. Put this in Desmos, and we got it. The result of that division to the 1,000th, we're looking at the 6, that'll make the 1 a 2, is 0.712. And now we can put that together and make the equation in the form of y equal a times b to the x. It would be y equals 0.712 times 1.331 to the power of x. And then we'll check our answer. To check our answer, what we do is go back to our original points and remember that they are x's and y's. X, y, plug in the x and see if you get the y. Because we've rounded, our answers won't be perfect, but they will be very close. And you can see that when I plug in 12 for x, I get very close to 22, that's that one, for y. And when I plug in 17 for x, I get very close to 92 for y. I know I'm correct. Question 4 is a quick one. All you need to do is plug in these x values. Plugging in 0, 3 to the 0th is 1. Plugging in 1, 3 to the 1st is 3. And plugging in 2, 3 squared is 9. And all you need are 2 points when you graph this in Desmos. We get a graph that looks like this. Here, when we plug in 0, it's 4 times 3 to the 0th, which is 4 times 1. Plugging in 1, 3 to the 1st is 3. 4 times 3 is 12. Plugging in 2, 3 squared is 9. 4 times 9 is 36. That's off our graph. And there's a rough sketch. All you need are 2 points again. Just drag between them and make your curve. Notice again that this is the y-intercept, 4. This is the common ratio. And because it's greater than 1, we're increasing. This is growth. In question 9, x is going to be the opposite. If x is the opposite, a point over here becomes over there. And we can see this will be a reflection over the y-axis. We see that it's horizontal. X has been replaced by 2x, and horizontal is the inverse. This is actually a compression by a half, a horizontal compression by a half. All you really need to know here is that you're going to plug in some values, and all you need are 2 to create this graph. Notice the values that I chose. 0, because that's easy. Negative 2 times 0 is 0, and 2 to the 0th power is 1. But then I chose some negatives because those would be easier to work with. Because when I plug in -1, -2 times -1 is +2, and it becomes 2 squared, which is 4. And when I plug in x is -2, -2 times -2 is +4, and 2 to the 4th is 16. And wanted to see what y was like when I plugged in a positive x. And an easy one, I thought it was a half, because when I plug in a half, -2 times a half is -1, and 2 to the negative first is 1 over 2 to the first, or 1/2. 1/2 is one of the points on the graph. Graphing those points, we can see how it's a reflection over the y-axis. Question 10 is an interesting one because of the negative again. What that negative does is flip that fraction. When I plug in x is 1, it becomes y equal 1/3 to the negative first, which becomes y equal 3 over 1. In other words, this fraction gets flipped every time because of the negative power. When we plug in 2, it becomes y equal 1/3 to the negative second, which is y equal 3 over 1 to the second, which is really just 3 squared, or 9. And when I plug in 3, it becomes 3 over 1 cubed, which is 27. And then I also picked a negative to see what would happen. When I plug in -1, it becomes the opposite of -1. And we get y equal 1/3 to the first power, or just 1/3. You should get a graph that looks something like that. The parent function, this would be the parent function, of an exponential equation has the x-axis as the asymptote. That line forever approaches the x-axis. If I do a horizontal transformation on that, that means I'm going to move it left and right, that has absolutely no effect on the asymptote. So the asymptote is the equation y equals 0. It's the x-axis. In question 14, the parent function would be y equal 2 to the x. That's this one here, and notice it approaches the x-axis again. The x-axis is our asymptote. That's y equals 0. And when I do a horizontal transformation, it has no effect. It moves it left and right. Left and right doesn't matter. What does matter is this -1. This is a vertical transformation. It takes every y value and moves it down 1. And that's why this equation here is down 1. And the asymptote then gets moved down 1. And it becomes a line y equal -1. A horizontal line through -1 on the y-axis. For question 19, the parent function would be y equal the log base 10 of x. Reminder, if there's no base, it's base 10. That would be this line right here. Notice the asymptote is the y-axis. The equation of the y-axis is x equals 0. If I replace x with x plus 2, this is the equation we have in this question, that's a horizontal transformation. Horizontal transformation moves things left and right. That does have effect in this case on the asymptote because the asymptote is vertical. We can see then what happens. Remember that what happens if it's horizontal is the inverse. What happens to the points, what happens in the equation are inverses of each other. So rather than moving this 2 to the right, it actually moves it 2 to the left. And that vertical line that this graph forever approaches is the line x equal -2. In question 22, our parent function is a log base 2 of x. Look at the transformations that were performed. We have a horizontal transformation, and that, remember, is the inverse. So -3 actually moves it to the right 3, horizontal, right 3. Here we have a vertical transformation. The -1 moves everything down 1. That doesn't affect the asymptote. A vertical transformation does not affect the asymptote for the log, but a horizontal one does. What I've done is move everything 3 to the right, and the equation of that asymptote is not x equals 0 anymore, it's x equals 3. For question 25, our equation is the natural log of x. That's the same thing as the log base e of x. No difference. And let's take a look at a simple example here. I just want to point out why you have an asymptote at x equals 0 for the log function. It's that y-axis. If I try to plug in x is 0 into any log equation, I've got a problem. Write this as an exponential expression. The base would be 10. A log is an exponent, and the exponent, I don't know what it is. It's that question mark. But 10 to some power would have to equal 0. Think about that for a moment. Is 10 to any power or any base, like e, which is 2.7 something, is e to some power 0? It's not possible. That's why you have an asymptote there, because it can't be that number. It gets closer and closer and closer to it, but it can never be that number. Here's the graph of the natural log of x, the log base e. Notice it doesn't look any different than any other log graph that we've looked at. And because there's no transformation, no horizontal transformation, the asymptote is still the y-axis. It's the equation x equals 0. And question 27, our last one here, has some transformations going on. We know that in y equal the natural log of x, that we just looked at that in the previous question, that the asymptote is the y-axis, or the equation is x equals 0. And the reason for that is I can't take the natural log of 0. There's no power. E to some power makes 0. That doesn't work. There is no power of e that makes 0. So I can't plug in 0 there. That's where the asymptote is. When I look at this equation then, what I know, the natural log of 2x minus 1, is that this thing can't be 0. 2x minus 1 cannot be 0. What value of x would make it 0? Well, let's solve this thing. 2x can't be, add 1 to both sides, 1, divide by 2, and x cannot be 1/2. Because if I plug in 1/2, I get 0, and I can't take the natural log of 0. 2 times 1/2 minus 1 equals 0. That can't happen. And when you graph this, what you're going to see is that it will forever approach the line x equal 1/2, but will never actually reach it. Let's look at the graph. Here's the graph of the natural log of 2x minus 1, like in our question. Notice how here's a half right between 0 and 1. The asymptote is x equal 1/2.